Today we're going to be looking at how to calculate the theoretical length of a mainspring given the dimensions from a watch. The formula in order to calculate the length of a mainspring is as follows. L equals pi times big R squared minus little r squared over 2 times E. L, that's the length of the mainspring. The big R represents the radius of the inner wall of the barrel drum. The little r represents the radius of the barrel arbor. Pi is a mathematical constant. We'll just use 3.14 to represent pi. E is the thickness of the spring. All of these measurements are going to be in millimeters. So I drew a picture of a barrel up here with the arbor inside of it. When we calculate this, we're going to use our calipers, and we're going to measure across the inside of the barrel to get that diameter. We're going to measure across the barrel arbor to get its diameter. And we'll measure the spring to get its thickness. Now, we're calculating the length of the spring, so we assume the spring is broken to the point that we can't really measure its length. But we should be able to have a piece we can measure its thickness. Okay. I'll walk you through calculating this problem, and then we'll come back and we'll look at why this formula works, and then we'll give you a problem so that you can try it on your own. So for our first problem, we're going to measure our barrel, and we have a barrel whose diameter, inside diameter of the barrel wall, is 9.3 millimeters. We measure across the arbor, and the diameter there is 2.80 millimeters. And when we measure the spring, its thickness is 0.1025 millimeters. Now at this point we need to be careful. With our tools we were able to measure the diameter of the barrel and the arbor. But our formula calls for the radius of the barrel and the arbor. So in order to convert a diameter to a radius, we need to divide by 2. And whenever you have one of these problems, you need to be real careful to make sure that you have, if you're using diameter or radius, that you're using the correct one. Okay. So we're going to go ahead and plug these numbers into our problem. L is equal to pi, which is 3.14. We need to get this, the radius, so we need to divide that by 2. That's going to be 4.65 squared minus, divide that by 2, 1.4 squared. The whole thing divided by 2 times the thickness of the spring, 0.1025. All right, we'll go ahead and start carrying out this problem. We'll start by calculating the inside of the parentheses there. 4.65 times 4.65 is 21.6225. And 1.4 times 1.4 is 1.96. Okay. We'll do that subtraction there. 3.14 times, when we subtract 21 minus that, we're going to get 19.6625. Now we'll do the multiplication across the top, and we're going to get 61.74025 over 2 times 0.1025. We'll do the bottom side, the numerator. We multiply that out, and that's 0.205. And then last, we just have to take our calculator and divide this number by this number, and you get 301.17. Got to remember always to put our units, and if you've ever measured or ordered a mainspring, you're not going to get it down to the 100th of a millimeter. So in this case, the acceptable answer is 301 millimeters. At this point, we want to pause and we want to think about whether this answer is realistic. We have a barrel that was about 9 millimeters in diameter. That's a fairly standard barrel. So we would expect the length of this spring to be something similar to something we've ordered in the past. Typically, when we order mainsprings, we order them in inches for the total length. So we want to quickly convert this to inches. There's about a little more than 25 millimeters in an inch. So if we were to divide that, this is going to be approximately 12 inches. That seems pretty reasonable for a spring in a wristwatch. So that seems like a reasonable answer. 301 millimeters would be the length of the spring for this watch. Okay, so now we're going to go ahead and look at this equation. It's wonderful to have a formula that you can plug numbers into, but we're going to take a moment to find out where this formula comes from and why it can show us the theoretical length of a mainspring in a barrel. We'll take a look at the picture of the barrel here. When you're putting a mainspring, you're designing a watch and you're putting a mainspring in there, you want the mainspring to provide enough power for the watch. But you also want to capitalize on the longest run time for the watch as possible. You want to make this barrel turn as many times as possible while delivering enough power. So the engineers determine what the thickness of the mainspring should be, and then they design around it. The mainspring needs to occupy half of the area inside of this barrel minus the space taken up by the arbor. That's so that when the mainspring is fully relaxed in the barrel, it's against the outside wall, it takes up half the space. And when you wind it, all of that mainspring is going to move to the inner half of the barrel, coiled up tight around the arbor. And if the mainspring can move that full space, you'll get the maximum number of turns possible. So in order to do that, we need to find out the size of that area. And that's essentially what this formula does. The area of a circle is calculated by the mathematical formula pi times the radius of the circle squared. So, come back here, when we have pi times the radius, the outside radius of the barrel, that's going to be the area of the entire inside of the barrel. And we're going to subtract the area taken up by the arbor. That's pi times the radius of the arbor squared. So this formula here will take the whole area of inside the barrel minus the amount taken up by the arbor. If we take the pi and move it out, regroup this, you end up with pi times r squared minus r squared. And you'll notice that is the top portion of our formula. The top portion of the formula just tells us how much area is inside the barrel not occupied by the arbor. We want our mainspring to occupy half that much space. And in order to do that, we're going to take that and we're going to divide by 2. So now we know how much is half of the area inside. All right, so then how do we take that and then get the length of the mainspring out of it? We're used to seeing mainsprings when they're all coiled up like that. But a mainspring is just a long rectangle. If we stretch it out flat, you just have a very long, very skinny rectangle. The area of a rectangle, is length times width. In the case of our spring, the width is the thickness of the spring. The length is what we're trying to figure out. So the area of that is length times the thickness of the spring. And the area we want it to occupy is this number right here. So we can take this and we can do the length of the spring times the thickness of the spring is equal to this formula right here. And if we divide both sides of our equation by E, these two will cancel each other out. And we're left with the length of our spring is equal to pi times the radius of the barrel minus the radius of the arbor squared divided by 2 times the thickness of the spring. Now, in actuality, engineers have determined that you get a more efficient system when the spring is 20% longer, but that is impractical. Theoretically speaking, the best idea is to have it equal to this, half the area inside of the barrel minus the area taken up by the arbor. So what do you do if you don't have the spring at all and you don't know how thick it is? As a general rule, the thickness of the spring, and this was in vintage watches, is about 1/30 of the diameter of the arbor. The diameter of the arbor. This varies a little bit. Higher quality watches, they're more efficient. They don't need as strong of a spring. So if you're looking at an old pocket watch that is a 21 jewel or a 25 jewel pocket watch, this number is probably closer to 1/32 the thickness of the arbor. And if you're looking at a low quality, a 7 jewel pocket watch, it's probably closer to 1/27. If we're looking at a modern watch with an alloy spring and a very efficient system, these numbers won't work at all. Luckily, we have manufacturers who have published these values. We don't typically have to calculate the length of the mainspring on a modern watch. We can just find that information in the technical document. But if we're looking at an old pocket watch or something like that and we just don't have the spring, these numbers will get you close enough to determine both the thickness of the spring and then, with the equation, the length of the spring. Okay, so we walked through one problem together, and then I demonstrated where this formula comes from, why it works for determining the length of the mainspring. Now I'm going to give you a problem that you can do on your own. Pause the video, and then come back, and we can check it, work it out together, and we can see whether the answer is correct. So for this problem, we're going to get a different barrel from a different watch. We're going to measure it. The diameter is going to be 7.6 millimeters. That's the diameter of the inside of the barrel wall. The diameter of the arbor is going to be 2.20 millimeters. And the thickness of the spring is going to be 0.08 millimeters. At this point, go ahead and pause the video. Go through the steps that I demonstrated earlier with the formula right here. Once you've got an answer, go ahead and start the video back up. We'll walk through the problem together. You can see if your answer is correct, and if you made any mistakes, you'll be able to see where you made those mistakes. So go ahead and pause this and come back when you're done with the problem. Welcome back. I assume you paused the video and you already did the math. You've got an answer. Let's walk through it together and see if your answer is correct. So first thing we're going to do is we're going to remember when we measured our barrel, we had diameters. And we need to use radius in our formula. So let's go ahead and plug our numbers into our formula. Length equals 3.14. Now the radius We have to divide that by 2. 3.8 squared minus 1.1 squared. All of that divided by 2 times 0.08. All right, we'll go ahead and perform the squared operations here. 14.44 minus 1.21. We'll do our subtraction inside of the parentheses. We get 13.23. Carry that out. Pi times what's inside the parentheses, 41.5422 over 2 times 0.08. We'll work on the numerator now. It's going to be 0.16. Now we just have to do that last division problem there, and we're going to get 259.63, or 259, we can round it up, 260 millimeters. Now again, we're going to do that little check. 260 millimeters. It's a little shorter than the other one. It was a smaller diameter barrel, so that makes sense. That's going to be 10.5 inches. Again, a very reasonable length for a spring in a wristwatch, especially if it's a smaller wristwatch. So if you've got that answer, you did it correctly. If you didn't get that answer, you need to go back and look at these steps and figure out where you made your mistake and practice again. I'm going to go ahead and give you another problem, and you can go ahead and try that one again. This time I won't walk through it. You can pause the video and we'll just have the answer when you get back. Okay, here's one last problem for you. You have a watch with a broken spring in it. The inner diameter of the barrel wall is 11.55 millimeters. The diameter of the barrel arbor is 4.0 millimeters. And the thickness of the spring is 0.135 millimeters. I'll write those down quickly. Diameter of the inner barrel wall, 11.55 millimeters. Diameter of the arbor, 4.0 millimeters. Thickness of the spring, 0.135 millimeters. Go ahead and pause the video. Plug those numbers into the formula. Get your answer. Come back to the video, and we'll have a response for you. Okay, so I assume that you paused the video, you ran through the numbers, you plugged them in the equation, and hopefully you got an answer that was 345 millimeters. This was a larger barrel than the other two examples, more of a pocket watch kind of barrel. So here we've got, something that's more like a 14-inch spring, a longer spring that would be appropriate for a pocket watch. If you have any more questions, all of this information is covered in the textbook Theory of Horology, which is available for purchase from AWCI at our webpage, awci.com. And this topic is specifically covered in Chapter 4, Section 2.5. You'll find other calculations you can do related to the mainspring there as well, and some examples of problems using derivatives of the same formula, but with different equations, where you could determine the thickness of the spring given the length and the barrel, or you could determine the diameter of the arbor if you were missing the barrel arbor but you had the spring in the barrel and these items. We hope to do more of these videos soon. Check back and you can learn some more watchmaking theory and mathematical equations related to watchmaking theory. Thank you.